We've done a couple examples so far in the section of showing that limits exist. And maybe the previous video using polar coordinates as a very multivariable calculus specific way to do things. So let's think about other types of problems. Does the limit as x, y goes to 0, 0 of y over x, does this exist? Spoiler alert, it's not going to exist. It's time to do some limits that don't exist here. So first thing to realize is that we're plugging in 0 and 0, we get 0 over 0 in a determinate form type of thing, so we can't simply substitute. We have to do something else to go on here. So the thing that we want to realize is the following. So it's been a while since I've drawn a picture. It's probably about time to draw a picture here. We're going to the origin here, 0, 0. And so we want to think about what's the limit along different paths as we go towards here. So we could go like this, we could go like this, we could go like this. So the limit exists, all the limits along all of these individual paths have to be the same. Here. But let's think about what happens if we walk along the positive x-axis. If we walk along the positive x-axis, so that's ... we're going in like that. Positive x-axis means that, well, x is positive, what's y equal to? Y has to equal 0. So if we're going in along the positive x-axis, we're guaranteed to have y equal to 0. So the limit would become, limit as x goes to 0 from the right of 0 over x. So you might think that this is like a 0 over 0 in the determinate form, but this expression here that we're taking the limit of is literally 0. It's literally 0. It's the constant 0. It's just always going to be 0 no matter what x is. This answer is going to be 0 here. So as we move along the positive x-axis, the limit here is equal to 0. Well, what happens if we, let's say that this is y is equal to x here. Let's walk along y is equal to x for positive x. So that would be, we're walking in along that line. Well, in this case, if y is equal to x, well, if y is equal to x, this is just x over x. And x over x, I think that simplification we could do, that's 1. Again, this is literally a constant, the limit of a constant. I don't care what else is going on there. The limit of that constant has to be that constant. This has to be 1. So let me ask you this. What does this limit, what is this limit equal to? Well, we walk along the positive x-axis, we're being told that the answer is 0. If we're walking along the line y is equal to x, we're being told that the answer is 1. And the limit can't be both 0 or 1. It can't decide between 0 and 1. And so, instead of saying it's both 0 and 1, and if I did other things, I'd come up with lots of different answers here, we say that the answer here is no. So our conclusion down here is the limit as xy goes to 0, 0 of y over x does not exist. And this is an example, this is an illustration of this test here, the two-path test for non-existence of a limit. So in general, if you want to show that a limit exists, show that a limit does exist, you could do it with algebraic manipulation or use like the polar coordinates as we did in the previous video. This is probably your best way for showing that your limit does not exist, the two-path test. The function f of xy has different limits along two different paths in the domain of f. as xy goes to x naught y naught, then the limit as xy goes to x naught y naught of f of xy, this does not exist. So how do we show that this limit does not exist? We pick two different paths going in towards the origin. We got two different answers here. And so we're able to conclude that our limit does not exist. So let's do a little bit more involved example here. Let us show that the limit as xy goes to 0, 0 of x squared over x squared plus y squared. Let's once again show that this limit does not exist. And we're going to do it using this two-path test. And so the our way of doing this is going to be a little specific way of applying the two-path test. What we're going to do is that we're going to check along all lines of the form y is equal to mx. So we're going to the origin here. Y is equal to mx. These are lines, with slope m that go through the origin. So we're going to replace y with mx. And so instead of just checking along two paths to the origin, we're going to check along infinitely many paths towards the origin. All lines, of slope m that go through the origin here. And it will be very, very quick for us once we do this to be able to show that this limit does not exist. Okay, let's go ahead and do that calculation. So what we're going to do is, so we have x squared over x squared plus y squared becomes mx squared. So we replace y with mx. And this is a single variable limit. As x goes to 0, y is m times x, y is also going to go to 0. So we're going to evaluate this limit, the limit as x goes to 0 of x squared over x squared plus mx quantity squared. Okay, so what does this limit equal to? X squared over x squared plus m squared times x squared. I can factor out an x squared from the denominator. X squared over x squared times 1 plus m squared. Those x squareds cancel out. So I have the limit as x goes to 0 of 1 over 1 plus m squared. And in terms of x, this m here is a constant. So if we've already chosen what m is, limit as x goes to 0, we don't care what's going on there. This expression is always going to be 1 over 1 plus m squared. So if we go along lines of the form y is equal to mx, limit as x goes to 0 of this expression is 1 over m squared. And so now it becomes very easy for us to check to see different values of m will give us different limits. If m is equal to 1 here, we get 1 over 1 plus 1 squared is equal to 1/2. If m is equal to 2 here, we get 1 over 1 plus 2 squared is equal to 1/5. And those aren't equal to each other. And so we have successfully shown that our limit here does not exist. So let me recap this method one more time. So this doesn't always work. We'll see in a future video that this method does not always work. But in order to effectively quickly apply the two-path test for non-existence of a limit, we just check infinitely many lines of the form y is equal to mx. replace y with mx here. So this just becomes a single variable limit. Do some simplification here. Your limit depends on m. So we check two different m values. You're going to get two different answers. So if our function has different limits along two different paths in the domain of f, the limit here does not exist. So m is equal to 1. That would be m is equal to 1 would be the line y is equal to x. The limit is 1/2. M is equal to 2. That would be y is equal to 2x. The limit is 1/5. Those aren't equal. Two-path test says this limit does not exist.